Hello everybody, welcome back. In this tutorial we're going to be covering quiz number 23, which talks about the restrictions of the elastic moduli. So overall, it shouldn't be too bad of a quiz, it's not too long, but it's a very important topic because these restrictions on the elastic moduli, they're very simple, and that's why they make for great midterm questions. They're one of those things that they're very simple to kind of understand. However, I always forget about them. I always have to go back and remind myself, oh, okay, these are the restrictions. But again, makes for a great midterm question. So please write them down somewhere because they're very good to know. All right, with that being said, let's jump into the theory. So last quiz, we talked about two types of materials. The first one was a linear elastic isotropic material, which we said, all right, this is a nice, easy material. And then we talked about a linear elastic orthotropic material. And we said, all right, well, it's not too bad, a little bit more complicated, but in the end, we, of course, could handle it. All right, so in this kind of part of the topic, we're going to discuss isotropic materials. Now, orthotropic materials have different restrictions than isotropic materials. However, as this course is more of a beginner course, we're not going to talk about orthotropic materials. We're going to focus on isotropic materials. So remember that we can actually determine the stresses from the strains of an isotropic linear elastic material, or vice versa, where if we have the strains, we can find the stresses, or if we have the stresses, we can find the strains because they share this nice relationship with this elasticity tensor in the center here, which we typically call C. Now, looking at C, we see that there are three components. There's the Poisson's ratio V, the Young's modulus E, and then the shear modulus D. And we said, all right, well, there's basically going to be three components that we need, or three parameters that we need. And if we have them, we can define this material. And we said, all right, well, hold on 1 second. That shear modulus G is actually a function of both the Young's modulus and the Poisson's ratio. Therefore, if we know the Young's modulus and the Poisson's ratio, we can simplify this down into two parameters, which is great. We said if we have a linear elastic isotropic material, we only need two parameters to define that material, which is wonderful, just E and V. And determining E and V using experimental tests is actually quite simple. So it's another benefit. So if I wanted to model something in real life, it's very easy to go to the structural lab. Let's say take a piece of steel, do a tension test, and from there I can determine E as well as V, and I can use that data in my computer models. All right, so let's kind of go off topic a little bit, or more like go towards the topic that we're discussing this week, and that is the restrictions on the elastic moduli. So kind of as a reference, let's think about that big elasticity tensor C. We said in its most general form, it had 81 components, and we said, all right, well, the stress and the strain matrix are symmetric, so therefore we were able to chop the 81 down to 36, and then we said, all right, well, due to the preservation of energy, the C matrix will be symmetric, so we went from 36 down to 21, and then for a linear elastic isotropic material, we were able to go from 21 all the way down to 2. So by incorporating real life behavior, we're able to make our analysis much simpler. And of course, we do the same thing with elastic moduli. We know that in theory, in mathematics, we can have them whatever they want. It's just a number. However, to make the deformation physically possible and to physically make sense in the real world, of course, we have restrictions. So where do these restrictions come from? Well, the first one is saying that the material is stable. The energy stored in the material under a state of strain is stored under a state of strain. What exactly does this mean? Well, let's say I have a material and I start compressing it. Well, of course, the strain is going to be in the direction that I'm compressing it. However, if I compress something and then somehow the uniaxial strain is in tension, well, that doesn't make any physical sense at all. And that's what it means by the material is stable. And of course, the second thing that we're going to want to talk about is a material that is deformable. So if I were to compress something, it's going to have strains. Let's think about a concrete slab, for example. When you guys are walking around, let's say NREF or eSurf or any of that, you're walking on a floor and you don't feel any of the deflections because it's a very stiff structure. However, you just walking on it, you guys will impose some strain on the structure. However, it's very small. That's why you don't experience it. However, I'm saying however a little too much. The point being is that when we put a force on something, it's going to result in some strain. Now, using these two restrictions, we're able to conclude two different things. The first one is the following limit of the Young's modulus, and that is that the Young's modulus must be greater than 0. Now, kind of the little keep away or takeaway here, greater than 0, not equal to 0, it has to be greater than 0. And the second one, which is mostly the focus of this quiz, is the Poisson's ratio must be between -1 and 1/2. Now again, just like the Young's modulus, it has to be between there. It cannot be equal to -1, and it cannot be equal to 1/2, and we're going to discuss why in the quiz. All right, guys, so that wraps up the theory. Let's jump into the quiz. So the quiz itself, nice, short, easy quiz. It's kind of just, again, talking about the restrictions on the elastic moduli, which, as I alluded to, is very simple. However, it's very easy to forget. So my recommendation is when you guys do the midterm, just take a little cheat sheet in and write on all of these elastic moduli restrictions. As you guys will see, they're not too bad at all. So let's look at question number 1. And question number 1 says concrete and steel are considered linear elastic. And then Dr. Sammer says isotropic materials, and that's kind of iffy. What I mean by iffy is that, yes, when we model these materials, we consider them to be linear elastic isotropic materials. However, naturally, are they actually linear elastic isotropic materials? Probably not. They're more orthotropic materials, and concrete especially has a lot of nonlinear behavior. But of course, for this class, and if you guys are ever doing simple modeling, then yes, we will assume things to most likely be linear elastic isotropic materials. And the reason why is because, of course, it's nice and simple. We only need 2 parameters to define them. So part A says, what are commonly accepted values of Young's modulus and Poisson's ratio for steel and concrete? And then part B says, consider a concrete cube of dimension L0, and if a force is applied on one face such that the length perpendicular to this face becomes delta L plus L0, or sorry, get delta plus L0, what is the length of the 2 remaining faces? So we're going to come down here and say, all right, well, part A, it wants us to discuss what steel and concrete is. So for steel, it's actually a lot nicer than concrete, where it's commonly accepted that the Young's modulus is 200,000 MPa. And as you guys will see when we start discussing about design, we always keep things in MPa. So I know Dr. Sammer likes to throw around GPa a lot, but when we talk about design, everything's always in MPa. And the reason why is because if we keep things in MPa, then our units will always be newtons and millimeters. It makes converting a lot easier. Now that's the Young's modulus, and that's again for design. If I were to design a steel building and I needed the Young's modulus, I would use 200,000 MPa, and that also comes right from the Canadian code book for steel design. Now Poisson's ratio for the steel is also a lot more nicer than concrete, where it's commonly accepted that it is 0.3. So steel, a lot easier than concrete, where the Young's modulus is 200,000 MPa and the Poisson's ratio is 0.3. Now, if I were to go to concrete, as I was kind of alluding to, it's a lot more iffy, if you will, where the Young's modulus and Poisson's ratio of concrete varies all over the place depending on who did the tests and where. So for the Young's modulus, what I'm going to do is I'm going to use the code equation. So the concrete code actually gives us an equation for the Young's modulus of concrete, which is equal to 4,500 times the square root of F prime C. So this F prime C right here is the compression strength of concrete. How do we get that? Well, I take a cylinder of concrete and I crush it. And that peak strength, that is what I call F prime C, or my compressive strength of the concrete. And this usually ranges from 30 MPa all the way up to higher strength concrete, which is around 70 MPa. So in the end, I get the concrete Young's modulus to be around 25,000 MPa. So as you guys can see, it's a lot lower when compared to steel. Kind of a little fun fact. Now, the second thing that we're going to want to discuss about concrete is the Poisson's ratio. And just like the Young's modulus, it's all over the place. I've seen it as low as 0.1, and I've seen it as high as 0.25. However, kind of the ground that most people consider a reasonable value would be around 0.2. So I'm going to write that the Poisson's ratio, it's probably around 0.2, and these are generally safe bets if you guys are going to design. This is exactly how you do it. So now let's consider part B, which says a cube of dimension L0, and we have a force applied on it. So what I'm going to do is I'm going to draw this cube just simply in 2D, or just as a square, because since it's an isotropic material, the behavior is going to be the same no matter which way I rotate it, so I'm not going to worry too much. So we have a cube, and of course it's saying that we're applying some tension on it right here. So we're going to have uniaxial tension. And originally it says that our lengths of the cube are L0. So let's switch over to green. We're saying that this face right here, this length is going to be L0. And of course the length going across the cube is also going to be L0. So it's a perfectly square cube. And what we're going to do is we're going to examine it after. So as you guys can imagine, what's going to happen is that this is going to get a little bit longer, and I think I made it a little bit too long, so I'm just going to shrink it a bit. So it gets longer, but it also gets skinnier at the same time, or at least this is what we expect with most materials. And I say most because, as you guys will see, we're going to discuss a very special type of material where the opposite happens. So again, this is our load, and we know that the new length of this cube is now, and I'm not sure if this is the same green. Oh, it is the same green. Perfect. We know that the new length of this cube is going to be L naught plus delta. So delta is that additional length that we get. And now the question is what is this right here? So this right here, well, as you guys will see, it's very easy to tell. It's going to be L naught minus the Poisson's ratio multiplied by the extension. The Poisson's ratio for concrete, and actually I'm going to take this out because I'm going to run out of room really quick and it's going to look pretty messy. So I'll say this comes down here. And as we'll see, it's going to be L naught, and then it gets smaller. So we're going to subtract the Poisson's ratio. You said that for concrete, it's most likely around 0.2, and then we times by the extension, which is delta. So that would be the new width of the cube, L naught minus 0.2 delta. And I'll put in a different color right here. This is the same as just saying minus the Poisson's ratio multiplied by the expansion right there. So a nice easy question, and I forgot to label this as this is, of course, part B. So it's a nice little introduction in what is the Poisson's ratio and why do we use it, because then again, if we know the behavior in one direction, the Poisson's ratio will tell us the behavior in the other directions. So that concludes question number 1. Let's go into question number 2, where we start to discuss the effects of the Poisson's ratio in a bit more detail. So question 2 says, consider the limits of the Poisson's ratio for a linear elastic, and of course I forgot to mention, but it's an isotropic material. And as you guys will see, a lot of these questions that you'll see in the midterm, there's very little chance of them mentioning isotropic materials, but for your course, just assume it's isotropic. That's the simplest form. And again, this is an introduction course. This isn't anything advanced. If it is an orthotropic material, trust me when I say you will know it's an orthotropic material. Remember last quiz when we talked about the orthotropic piece of wood? It was a nightmare. That's how you tell if it's orthotropic. However, right now we're just considering the Poisson's ratio limits for a linear elastic isotropic material. And what we're going to do is we're going to discuss each of the scenarios and discuss where these limits come from. So right above here, I'm going to talk about the limits. So we know that Poisson's ratio must be between -1 and 1/2. And what we're going to see coming down here is we're going to kind of derive these limits a lot of the times. All right, so we're going to come down here and says, part A says, a material is incompressible. And what this means is the bulk modulus K is equal to infinity, resulting in no volumetric strain accompanying a hydrostatic stress. All right, so let's figure out what limit of the Poisson's ratio does this correspond to. So I know that the bulk modulus K can be written as a nice simple formula where it's E divided by 3, 1 minus 2 times the Poisson's ratio. And of course I said we have E up top there. I always draw the bottom first because it makes it a little bit easier to figure out how to make E centered in the equation. And of course we're talking about when this is equal to infinity. Well, the only way that this is going to be equal to infinity is if we divide by 0. So therefore 3 multiplied by 1 minus 2 times the Poisson's ratio has to be equal to 0 for this to hold true. Well, if I move 3 to the other side, well, 3 times 0 is still going to be 0. So I'm going to have 1 minus 2v is equal to 0. And I can simply rearrange, and I get that my Poisson's ratio for this case is simply going to be equal to 1/2. And what I'll do is I'll draw a little box around it so you guys can know exactly. That's the furthest thing from a box. Let's try that again for a second time. All right, that's a little bit better. So this corresponds to the case of V is equal to 1/2. And you're saying, well, Clayton, that kind of looks like the limit. Well, it kind of looks like the limit, but it's not the limit. So when we go up to the limit, as seen at the top of the page here, remember we say that it has to be less than 1/2. We say it cannot be equal to 1/2. It has to be less than 1/2. So if I have V is equal to 0.499999, completely fine. If I had V equal to 1/2, well, then that doesn't work at all. So that's just something to keep in mind, and that is part A. So let's switch back to the pink and come down and look at part B. So now it's the same scenario, except it says if we have a negative bulk modulus K, which results in positive volumetric strain accompanying a negative hydrostatic pressure. So this means if we're taking a cylinder, let's say, and we're compressing it from all sides, well, we expect it to, of course, be compressed. However, if we have a negative bulk modulus, we're saying that under all that compression, it somehow expands, which of course doesn't make sense, which is also why we say this is physically impossible for linear elastic materials. So if it's impossible, then it makes our lives easier because then we can kind of play around with the math and make our analysis a little bit smoother because we now know some restrictions. Well, how do we prove this? Well, we know that K again is equal to E divided by 3 multiplied by 1 minus 2 times the Poisson's ratio. So again, we have E on the top here. And we're saying that this is going to be negative. So we're going to have less than 0. So of course, E, this will always be positive for a linear elastic system. So the only way that this can be negative is if that bottom component is less than 0. So therefore, we can say that 1 minus 2 times the Poisson's ratio has to be less than 0 for this to hold true. Well, again, just like before, if I move 3 to the other side, it's just going to be 3 times 0, which is 0. So I get 1 minus 2 times V is less than 0. Therefore, 1 has to be less than 2 times V, and therefore V has to be greater than 1/2 for this to hold true. And this is why we have the statement that V has to be less than 1/2, because if it's greater than 1/2, that means that we have a negative bulk modulus. So that's the kind of the two cases for the bulk modulus. Let's go down to the next case, which starts talking about the shear modulus. So the first one, and I'll switch back to pink, is a material is rigid and shear. Therefore, our shear modulus G is equal to infinity, and this results in non-zero values for shear stresses causing shear strains. So how are we going to derive this one? Well, we're going to, again, look at the formula for our shear modulus. So G is equal to, and on the bottom here, I'm going to have 2 times 1 plus V, and on the top, just like before, we simply have E. And we're solving this where this is equal to infinity. And just like before, the only way that this equation is going to be equal to infinity is if we divide by 0. Therefore, 2 multiplied by 1 plus V is equal to 0. Well, if I move 2 to the other side, it's going to be 2 times 0. It's still going to be 0. So I get 1 plus V is equal to 0. Just move the 1 to the other side. This is the case where V is equal to -1. So this goes back to our case before where we said, well, I thought that we could have -1. Well, the truth is we can't have -1 because if we come back up and look at the limit, we say it has to be greater than -1. We don't have a greater than or equal sign. We simply have a greater than sign. So V has to be greater than -1. It cannot be equal to -1. And the reason why, that results in a material being completely rigid and shear, which is just not true, to put it simply. All right, moving on, we're going to kind of consider the same case now, but a negative shear modulus resulting in a positive shear strains for accompanying negative shear stresses, which again is physically impossible for these linear elastic materials. So I'm going to come down here and I'm going to do the same thing as before, where I say J is equal to E, and I'm being bold typing the E first, and then 2 multiplied by 1 plus V. Well, again, linear elastic system, we know that E is going to be greater than 0. Therefore, the only way this could be negative is if the bottom, which is 2 multiplied by 1 plus V, is less than 0, or the bottom is a negative component. How do I solve this? Well, I'm just going to throw 2 to the other side. It'll cancel out. Therefore, I get 1 plus V has to be less than 0. Or I get V has to be less than -1 for this statement to hold true. So this comes for the limit that V cannot be less than or equal to -1, because if it's less than -1, we have positive shear strains for negative shear stresses. If it's equal to -1, well, then it's completely rigid and shear, which both cases don't really work. Now we're going to talk about the fun cases. These are cases that we will kind of come across, well, not really come across, but these are just fun cases. So the first one is no lateral strain when a material is pulled longitudinally. And you're saying, okay, Clayton, well, this doesn't sound like a bad one. What exactly does this mean, though? So again, let's say that I have a nice square, and I am trying to annotate the square, not move it around. But let's say that I'm pulling this in tension. So come down here and just like this. Well, what this question is saying is what happens if I pull this square in tension? And what happens is I get the following. So again, we expect it to get nice and long and it expands. So this will still be my force like that. And what this question is saying is that if this originally starts off as, I'll just put this here, this distance we say is L naught. Well, after we expand it, it's still going to be L naught. So there is no lateral expansion or contraction under this system. Well, what this means is that the Poisson's ratio must, of course, be equal to 0 because we're seeing no expansion or contraction in that direction when we pull it in tension in the axial direction. So this is kind of a nice, easier case where the Poisson's ratio is equal to 0. Now let's talk about the last case of question 2, and this is the most fun case because this is something that can actually happen. And it's one of those things that you look at and you never expect it to happen, but when you go, oh wow, this is actually really cool. So what happens in this case is, again, we're going to have a nice square, and oh, it actually looked pretty good this time. And we're going to pull it under tension. So under tension, I'm going to draw my nice little arrow showing you guys that yes, this is indeed tension right here. And what happens when we pull it under tension, we expect, of course, it to get longer. But in this case, it'll also, oh, that is not what I wanted at all. But in this particular case, it also gets thicker, which is something that we don't expect. When we pull most materials, and I say most of them because these are the materials that we're most commonly accustomed to, they get thinner as we pull them in tension. However, in this case, it gets thicker, and I'll switch to this color. So let's say that I'm comparing these two directions. So I'll start off at the original one. So let's say that originally before we pull, this starts off at L naught. Well, after we pull, this becomes L naught plus something, let's say delta. So as we're pulling it in tension, it gets thicker or expands the same time laterally. Well, in this case, our Poisson's ratio must be negative. So when the Poisson's ratio is negative, this is how this behavior occurs. And I don't really know how to pronounce this word, but this is called one of these materials. Again, I don't know how to pronounce that. I'm going to save myself the embarrassment. Or you know what, maybe for you guys, because you guys are special, I'll try I'm just going to say it's an exotic material. It sounds close enough. So one of these materials, this actually happens. And the best way I can think of these materials, you guys know that little ball? I'll put a picture of it on the screen right now, but one of these balls, you pull it, so it's going in tension. As we can see, it expands laterally. So this is how I always think of these materials. And again, this means that the Poisson's ratio, V, has to be negative. But remember, at the same time, we also have the limit where V has to be greater than -1. So this is going to be the case for this question right here. And with that, that concludes question number 2. Therefore, we're actually done the majority of this quiz. But question number 2, this is what you guys are going to want to remember. Question number 2 is questions that appear on the midterm so frequently. A question exactly like type F here, or part D, or I don't even know what to call it. But this exact question, very popular midterm question, so please remember this. All right, guys, so now we're going to jump into questions 3 and 4, which kind of talk about the volumetric strain and how they behave in isotropic and orthotropic materials. So question 3, great midterm question. So something like this looks like it could be right from your midterm, and honestly, between us, I'd be surprised if this exact question doesn't appear on your second midterm. Or I'm not sure if this material will be in the final. I think this will be the second midterm material. So question just like this, guaranteed to expect it, because it's a nice simple question and it discusses concepts that are very relevant to these limits on the elastic moduli. And it says, in a uniaxial state of stress, an isotropic linear elastic material subjected to a tensile loading sigma 1,1. If all other stress values are equal to 0, and I'm going to highlight this because this is very important, if all other stress values are equal to 0, the total volume is either A, increasing, B, decreasing, C, stays the same, or part D, the information provided is not enough to answer this question. And I don't know about you guys, but when I have questions that have that part D, I really hate it because it always makes me second guess everything. But I will tell you right away, for this type of question, it's not going to be part D. The volume will either increase, decrease, or stay the same. Very unlikely that it stays the same though, because that implies that something is rigid, which we don't really talk about because it's not realistic. So let's try and figure out what exactly is going to happen here. And what we have to realize is that when we're comparing the volume or how it changes, we want to look at something called the volumetric strain, which is epsilon sub v, and this is equal to epsilon 1,1 plus epsilon 2,2 plus epsilon 3,3. So in the end here, this volumetric strain is simply going to be the trace of our strain tensor. It's the sum of all those diagonal components, and all the off-diagonal components, who cares? We're just considering about these ones. Now, if we remember our question, we were given the value of stress, which is sigma 1,1, and that's all our stress tensor is, but that was it. So it comes back to quiz number 23, I believe. I don't know if this is 23. No, this is 23. It goes back to quiz number 22, where if we have stresses, how can we find the strains? And what I did last quiz is I showed you guys the matrix method, where we were able to put in values of stresses and use that C matrix to determine our values of strains. And I kind of hinted last time that you guys would probably make fun of me saying, Clayton, why are you doing the matrix when there actually is very nice equation relationships that you can use instead? So I did the matrix on purpose last time because right now I can show you guys the equation method. So for a linear elastic isotropic material, the strain in the 1,1 direction is simply going to be equal to sigma 1,1 divided by E. And since it's an isotropic material, we only have one value of E, so that's why I just have E. And then, actually not plus, get rid of this. It's going to be subtracted by the Poisson's ratio times sigma 2,2, again, divided by E. And as you guys will quickly see, everything is going to be divided by E, minus the Poisson's ratio sigma 3,3, all divided by E. All right, so not too bad. We remember the question. It says that the only thing that this is subjected to is sigma 1,1. Therefore, sigma 2,2 and sigma 3,3 are 0. So what I'm going to do on the top here, I'm just going to set a reminder that sigma 2,2 is going to be equal to sigma 3,3 in this case, which is equal to 0. And that's great because we can cancel this out and we can cancel this out. Therefore, our epsilon 1,1, or our strain in the 1,1 direction, is simply going to be our stress 1,1 divided by E. So just a nice little simplification. And what we can do is we can come down here and say, all right, well, the strain in the 2,2 direction is going to be negative V sigma 1,1 divided by E plus sigma 2,2 divided by E, and then minus Poisson's ratio sigma 3,3 divided by E. So I hope that you guys kind of see the pattern with these equations. If I'm looking at 1,1, then what I do, and I'll highlight this to actually make it easier. If I'm looking at 1,1, well, then I know it's simply going to be my sigma 1,1 divided by E, and then all the other components that aren't 1,1, such as 2,2 and 3,3, I just simply add a V on it and then subtract it. So that's kind of the nice relationship. So it's very easy to remember these formulas. We don't really have to try and do a cheat sheet or anything. So now when I'm looking at sigma 2,2, my only positive component will be sigma 2,2 divided by E. All the other components will be sigma 1,1 or sigma 3,3. I multiply them by V and make them negative. So again, we already know from above that sigma 2,2 and sigma 3,3 are 0. So this is going to cancel and this is going to cancel. Therefore, my epsilon 2,2 is going to be equal to negative V sigma 1,1 all divided by E. So therefore, I already have two equations. I only need one more to solve for that volumetric strain, and that is epsilon 3,3. We go through, and I'm going to kind of go through the process of remembering these equations. So the first one is sigma 1,1. Well, 1,1 doesn't match 3,3, so I'm going to have to add a negative Poisson's ratio to it, sigma 1,1 divided by E. Go to the second one. Well, now I'm looking at 2,2, but my strain is in 3,3. So again, I'm going to have a negative Poisson's ratio multiplied by it. So negative Poisson's ratio, sigma 2,2 divided by E. And then my last one, sigma 3,3. Well, sigma 3,3 and epsilon 3,3, the 3,3's match. So in this case, I don't have to add the negative Poisson's ratio. I can just go plus sigma 3,3 all divided by E. And if you guys don't remember these equations, you guys can always just use the formulas from the matrices because it'll give you the exact same answer. These equations come directly from those matrices. Now, the final simplification, we say, all right, well, we know that sigma 22 is 0. We know that sigma 33 is 0. So all of this simplifies into negative v times sigma 11 all divided by E. And I can come down here and say, all right, well, now I have every component that I need for my volumetric strain. So E sub V is going to be equal to epsilon 11, which is sigma 11 divided by E, and then plus sigma 22, or sorry, epsilon 22, which we know is negative V sigma 11 divided by E, and then plus epsilon 33, which we now know, of course, is negative V sigma 11 divided by E. So this is our equation down below, and this is what we're left with. So I'm going to scroll down a little bit. I'm going to say, all right, this equation, well, of course, we can simplify this a little bit because in all of these terms, I have a sigma 11 and I have an E. So what I'm going to do is I'm going to pull out the sigma 11 divided by E. And then I'm left with, well, the first term, after I remove that, I have 1 minus, after I remove the sigma 11 E from the second term, I get minus V. And of course, from the last one, I have minus V. So in the end, my volumetric strain is equal to sigma 11 divided by E multiplied by 1 minus 2 times the Poisson's ratio. And now the question is this volumetric strain going to be positive or is it going to be negative? So what I'm going to do is I'm going to switch colors and we're going to compare the values in here because right away it doesn't look obvious. So if we look at the first term, which is this one right here, well, we know that sigma 11, it says it's going to be in tension, so sigma 11 is greater than 0. And then for a linear elastic material, E, of course, has to be 0 as well. So the first term will always be greater than 0. Let's look at the second term right here. We have 1 minus 2 times the Poisson's ratio. So right away, you guys can say, well, depending on the Poisson's ratio, it can either be negative or it could be positive. And that's true. However, remember, for isotropic materials, we have those limits on this Poisson's ratio. So let's change colors and let's look at the two limits. So let's say that V is equal to 1/2. Well, therefore, I have 1 minus 2 times 1/2. That's 1 minus 1. We have this term is equal to 0. Well, let's check out the other limit where Poisson's ratio is equal to -1. Well, then we have 1 minus 2 times -1, which is the same as 1 plus 2. We have this term is equal to 3. So in both of these cases here, because we know the Poisson's ratio is going to be between these two cases, this will always be greater than 0. So therefore, if my first term, sigma 11 divided by E is greater than 0, and my second term, 1 minus 2V is greater than 0, then I can say that my volumetric strain will always be, and I don't know why I did the equal sign, this will always be greater than 0. Therefore, the volume is actually going to always be increasing. So volume increases. And I'm going to come up here, so I just want to look. Well, if I look at part A, the total volume increases upon loading. That's exactly what I derived. So in this question right here, it's going to be part A. And that concludes question number 3. And this is for a linear elastic isotropic material. So now we're going to jump to question number 4, which deals with a linear elastic orthotropic material. All right, so question number 4 says, the limits of the Poisson's ratio for an orthotropic material can allow for a Poisson's ratio in a particular direction to take the values outside of a linear elastic isotropic material range. Therefore, those limits of the Poisson's ratio being between -1 and 0.5, well, they don't necessarily apply for an orthotropic material. For example, I can have a Poisson's ratio that is outside of those limits in one particular direction. If you guys do want to see where the limits come from, they're nicely kind of stated on Dr. Sammer's website. And if you guys take the grad school class, you guys will discuss more in depth about those limits. However, for you guys, it's not needed as much. As you guys will see, this question is nice and simple. It says, let the Poisson's ratio 1,2 equal the Poisson's ratio of 1,3, which is equal to 1. So again, we already know that this is outside of the limits that we had before. And it says, then, if a material is stretched in direction 1 with a tensile stress of sigma 11, A, the volume increases, B, the volume decreases, C, the volume stays the same, or D, the information provided is not enough to answer this question. So it's the same question as before, but instead of an isotropic material, we have an orthotropic material, but the process is still going to be the exact same. So I'm going to do is I'm going to come down here. I'm going to say, well, in order to solve this question, we need the volumetric strain, which is going to be equal to epsilon 1 plus epsilon 2 plus epsilon 3. All right, so that's not too bad at all. And then what we can do is there's nice equations, just like there was for an isotropic material, for an orthotropic material. So what I can do is I come down and just do all the three equations. So epsilon 1, well, this is going to be equal to sigma 1 divided by E 1. So the first key that we have to realize here is this is an orthotropic material. Therefore, the E, the Young's modulus, varies depending on which direction we're talking about. So in this case, we're talking about sigma 1, we're going to have to talk about E 1. Moving on to the second one, we have a minus Poisson's ratio again, just like before, but again, direction matters. So this can be minus Poisson's ratio 2 multiplied by sigma 2, all divided by E 2. Moving on, I can do the same thing for the sigma 3. I'm going to have minus Poisson's ratio 3 multiplied by sigma 3, all divided by E 3. So right away, there isn't too much we can do because it looks like it's really scary, but then we have to remember that just like before, we're doing a nice little uniaxial test. Therefore, sigma 3, and I don't know why I started with that one first, is equal to sigma 2, which is equal to 0. So just like before, the second and the third terms, they both cancel. Therefore, my epsilon 1 is going to be equal to sigma 1 divided by E 1. So as we can see, it's very similar to before, except instead of E, I just have epsilon 1. Now, sorry, I got E 1. So if we go epsilon 2, it's going to be, again, very similar to before, where we have negative the Poisson's ratio of 1 multiplied by sigma 1, all divided by E 1. And then we have plus sigma 2 divided by E 2. And then minus the Poisson's ratio V 3 times sigma 3, all divided by E 3. And you guys are saying, all right, Clayton, this looks pretty good because we know that sigma 2 is 0. We know that sigma 3 is 0. Therefore, in the end, we are left with negative Poisson's ratio 1 times sigma 1, all divided by E 1. Let me come down and say, all right, well, I just got to do that same process again for epsilon 3. So this is going to be equal to negative Poisson's ratio 1 times sigma 1, all divided by E 1, and then subtracted from Poisson's ratio of, 2, sigma 2, all divided by E 2. And then finally, we have to add on the plus sigma 3 divided by, and I don't know why that's so offset. Let me just fix that. You guys deserve better than that. E 3. So in the end, we know that just like the previous two equations, sigma 2 is going to be equal to 0, sigma 3 is going to be equal to 0, and we are left with the negative Poisson's ratio 1 times sigma 1, and all of this is going to be divided by E 1. All right, we're looking good. So now what we can do is we can take epsilon 1, epsilon 2, and epsilon 3, and substitute them into the volumetric strain. So I'm just going to scroll down a little bit to give me some more room. And I find that my volumetric strain, which is the sum of all three of those, is going to be equal to sigma 1 divided by E 1 minus the Poisson's ratio 1 multiplied by sigma 1, all divided by E 1. So as you guys will see, just like before, we're starting to get a lot of E11s and sigma 1s. And finally, we're subtracting epsilon 3, which is the Poisson's ratio 1 times sigma 1, all divided by E 1. So I'm just going to scroll down a little bit more to give me some more room and just focus on this equation. So let's simplify this a little bit. All the terms have an a sigma 1, 1, and they all have an E11. So I'm going to have sigma 1, 1 divided by E11. And when I factor that out, from the three terms, I have 1 minus the Poisson's ratio 1, 2, and then minus the Poisson's ratio 1, 3 as my volumetric strain. Now we can simplify this a little bit more, because if we scroll up to the top of the question, it gives us a nice piece of information that says let V12 equal to V13, which is equal to 1. So that's a very key piece of information, because I can come down to my formula here and say, all right, I'm going to switch colors. And this right here is equal to 1, and we know that this right here is equal to 1. Therefore, this whole thing is equal to sigma 1, 1 divided by E11. And then we have 1 minus 1 minus 1. So in the end here, that 1 minus 1 minus 1 is just simply going to be negative 1. So therefore, my volumetric strain in this case is equal to negative sigma 1, 1 divided by E11. Now let's try and think of what this would be. Again, from before, we know we're loading in tension. Therefore, sigma 1, 1 is going to be greater than 0. And just like before, E11, and this applies to E22 and E33, those all have to be greater than 0. That has to do with stability. That doesn't really have to do with the Poisson's ratio. So if those two values are always going to be positive, well, then this negative out in front will always ensure that my volumetric strain, so I'll say my volumetric strain in this case, so volumetric strain will be always negative, and therefore the volume will be decreasing. So negative, therefore in this particular case, the volume is decreasing. So I'm going to come down here. Oh, part B, that's my exact answer. The volume is decreasing, so I'm going to circle this. Now, I want to discuss something really quick, because when I look at this question, I remember I told you guys in question 3, that I really don't like answer D. Answer D makes this really suck, because it always has that little doubt in your mind that, hey, maybe I do not have enough information, or maybe I'm overlooking something. And part D would actually apply in an orthotropic material, which I hate. If we weren't given that juicy piece of information right here of epsilon, I can't even talk, V12 and V13 is equal to 1, we could not solve this problem. It was only because we knew what V12 and V13 are that we were able to solve this problem. So if we weren't given those, then we actually wouldn't have enough information. However, since we were generously given those pieces of information, we could solve this question. So that concludes question number 4, and with that, quiz number 23. So I hope it helped you guys. Again, these quizzes are for you guys, or these tutorials, they're for you guys. Hopefully it helps you guys. Hopefully it clears up all the questions that you may have. So thank you guys all so much for listening. I really appreciate it. I will see you guys in quiz number 24.